All right, AP students, welcome to your Unit 3 Solutions and Solubility Review. We have just spent time in Unit 7 talking about ice table problems or equilibrium problems. There are three main types, and we're going to transition now into looking specifically at calculating or determining the equilibrium constant for a dissociation reaction, which is its own unique kind of subcategory in equilibrium known as the solubility ion product constant. Anyway, KSP. But before we can do that, I just want to make sure that you guys are solid on your solution knowledge, your solubility knowledge, and your molarity calculation knowledge. So to begin, let's just start with the math problem. Determine molarity of ions in a solution. And of course, we know that a solution is a homogeneous mixture using stoichiometric relationships, i.e. molar ratios. So here we have calculate the concentration of all ions in the following solutions. So 0.35 grams of ammonium phosphate. I really hope you know your polyatomics, dissolved in 650 milliliters of solution. Okay, so for this one, what you should do immediately and recognize is that what we have is some amount in grams. So we're going to want to convert that to moles to determine concentration because molarity is equal to moles per liter. So we're going to do 0.35 grams times the molar mass of ammonium phosphate, which give me 1 second to look that up because I don't want to calculate it right now. Okay, so it has a molar mass of 149.09, okay, grams per mole, which means I'm actually going to shift it down because I want to cancel out my grams and put it into moles. And so that gives me the amount in moles of my solute ammonium phosphate. So let's see, I'll do the math really quickly through my little phone calculator, divided by 149.09. And we have a mole amount of 0.00235. And now what I want to do is I want to go from not just moles, but I want to get to concentration of my original sample. So I know that I am in 650 milliliters, and that translates to 0.650 liters. So I'm going to calculate that to get moles per liter. And I get that I have a molarity originally of 0.0036. Okay, 36 molarity of ammonium phosphate. Okay, NH4, PO4. All right. And so what I need to know now is what is the concentration of each ion? So now what I do is I take the concentration of my overall solute and I use the stoichiometric relationships revealed in the now subscripts of my ionic compound to determine the molarity of each ion present. So I have 0.0036 molarity of ammonium phosphate, okay, NH4, PO4. And I know that for every 1 NH4, 3 PO4, I'm going to have 3 NH4 plus, all right, ions or moles of ions, okay, or molarity of ion, right? Because it's per liter, it's the amount of moles per liter. So what I would find is that I do this simple stoichiometric unit conversion, and I would get that I have in concentration 0.011 rounded to the proper sig figs molarity of NH4 plus in solution. And I would do the same process with figuring out the anion concentration of PO4. So I'm just going to bring this down and say, hey, you kind of copy and paste all that down below. And I'm going to say, well, I know that for every 1 PO4, 3 minus, oh my goodness, not 3 plus, I have 1 compound of NH4 PO4, and I get a value of 0.0035 to the proper sig figs, molarity for PO4 3 minus ions present in solution. Okay, so for hopefully that seems like a really nice review. Now let's move on to calculating ion concentration when you mix two aqueous samples and therefore have to account for dilution. So here we have calculate the concentration of each ion in solution formed when 25 milliliters of 0.5 molar MgCl2 magnesium chloride is mixed with 10 milliliters of 0.60 molarity aluminum chloride. So first and foremost, you should notice that these two compounds are mixed, which means we are definitely going to have to calculate the diluted concentrations first. I'll write that in black. We're going to definitely do some diluted concentration calculations. But two, you should also notice that these share a common ion of Cl, a shared ion. Okay, Cl minus. So when we calculate the total amount of ion concentration from Cl, don't forget to sum it together. Okay, so let's go ahead and work through this problem. And what we do is I'm going to first address MgCl2 because it's the first thing. So I'm going to say, well, the original concentration of MgCl2 was 0.50 molarity. All right, but what we have it is that it was originally in a sample of 25 milliliters, but now we're in a sample of 25 plus 30 plus 10, which is 35 milliliters. So I'm going to multiply it by a dilution factor, which, by the way, this is just a rendition of M1V1 equals M2V2, where I move it around. All right, so that I have M1 times V1 over V2 to solve for M2, the new diluted, okay? It's the same simple mathematical process, okay? And I get that my diluted concentration is 0.36 molarity, MgCl2, okay? And so MgCl2, now what I'm going to do is I'm going to take that amount and do my stoichiometric relationship to determine the ion concentration. If you want to, you are totally welcome to do the chemical reaction. And what I would say is that for every 1 MgCl2, I have 1 Mg2 plus ion dissociated and 2 Cl minus ions dissociated. That might help you, but you could totally figure it out without actually writing out the equation because it's revealed in the molar ratios of the subscripts. All right. And then what you would do is you would simply do what we did above. You would calculate according to the stoichiometric or subscript molar relationship in terms of ion present in the compound. And you would get that if I originally had 0.36 molarity or molar MgCl2, I'm going to have 0.36 molarity of Mg2 plus. And I'm going to have twice that of the original molarity for chlorine ions because I need 2 chlorine ions for every 1 mole of compound. So I would say that I would have a concentration of 0.72 molarity Cl minus. All right, so now we're going to repeat all of this for the other. Okay, ionic compound A, aluminum chloride. So again, we're going to do the diluted factor. We need to dilute. And what we see is that I have an original concentration of 0.60 molarity, and I'm going to multiply it by the dilution factor of 10 milliliters over 35 milliliters, giving me a value of 0.17 molarity AlCl3. Now I'm going to, again, you don't have to do this, but you're welcome to clarify my molar ratio between ions produced. So I have 1 aluminum 3 plus ion produced for every aluminum chloride dissociated, and I have 3 chlorine ions produced for every aluminum chloride dissociated. And then what I do is I simply do my math. So I know that for every 1 mole of aluminum chloride, I have 1 mole of aluminum ions. So that means I have 0.17 molar aluminum 3 plus ions in solution. And that means I'm going to multiply my original concentration by 3 times to represent triple the amount of chlorine ion molarity. So I'm going to get a value of 0.51 molarity of Cl minus. Now I'm asked what's the total concentration of each ion. So I have my individual ion of magnesium 2 plus, aluminum 3 plus, and now I'm going to sum up, okay, my chlorine ions, and I get a value of chlorine concentration is equal to 1.23 molar chlorine ion, and that would be my answer. Hopefully this is feeling really good for you guys. Okay, so let's move on to now our review on solubility. Now that we know how to calculate ion concentration for a solution, we know how to account for dilution in a solution. Okay, let's remind ourselves solubility principles. So don't forget solubility, all right, is defined as the amount of solute, okay, that can be dissolved in a particular volume of substance, a specific output, specific volume or amount, right, of solvent. Oftentimes that solvent is water, but we can do it in other things. We have multiple units. Don't forget that we can have multiple units. Our preferred unit is molarity. We call this molar solubility. It's solubility related in terms of molarity, okay, which is moles per liter. So moles of solute dissolved per liter of solvent. We also have grams per liter, not as common, but totally possible, or grams per milliliter, just a rendition of it. Or you might even see it in parts per million ppm, although not as common at all in terms of AP. APES, I think that's far more common because we tend to measure the hardness of water in ppm, the presence of minerals in the environment. But all right, so if you feel the need to remember how to do a little bit more practice between converting between solubility units, feel free to pause me right now and go ahead and try this on your own. All right, so hopefully you guys took a moment to try these problems out. I just gave an outline of what your unit conversion would look like. You're gonna have some value, all right, for the molar mass relative to your particular species, manganese sulfide, and again, the molar mass relative to your particular species, lead iodate. And iodate is a polyatomic ion represented by IO3 with carrying a one minus charge. But hopefully you got these answers. And if not, you might want to go back to some stoichiometry problems and kind of remind yourself, but we're going to keep moving on. So now that we are solid, hopefully, on dilution calculations, solubility calculations, let's kind of remind ourselves when we think about solubility, the concept of dissolving, how does it connect with representing in a chemical process or a physical process? So obviously solubility can lead to a reaction, but generally we think of solubility as the mixing of particles. Therefore, it's a physical process in which your solute IMFs or attractions and your solvent attractions are broken to now form solvent attractions, right? That before, during, after. Okay. And so what we're going to look at is solubility's particular relationship, conceptual relationship with understanding dissociation reactions of ionic compounds in water, creating an aqueous homogeneous solution, and precipitation formation, right? So just as a one review, why don't you try writing the balanced chemical reaction for the following dissociation reaction. And remember, it's technically a physical reaction, but we kind of just treat it because this physical reaction of dissociation can sometimes lead to an actual chemical reaction where we get a precipitate formed. So go ahead and write the balanced chemical equation really quickly. Okay, so for the chemical or physical reaction represented in a chemical equation format, you should have gotten the following: that zinc carbonate, okay, solid, and I guess I should have specified this is zinc 2 because it's transition metal. Oops, sorry. Zinc 2 carbonate, solid, is going to dissociate into zinc 2 plus aqueous and 1 carbonate to minus aqueous, okay? And all right. And what we then look at is when we think about dissociation reactions involving now two ionic compounds in a mixture, right? Then what we have is a double displacement reaction. Oops, and I can spell displacement. That could turn into the potential of a precipitation reaction, if one of those do-si-do switches between the ionic compounds ions produces an insoluble or low soluble, okay, ionic compound. So let's quickly see. These low soluble would be precipitate favoring. Okay, precipitate favoring. So what we have here then is write the formula. Let's put this all together now of using the table and being able to write a dissociation for one ionic compound. Now put it together to two. And using our table, write the formula for the precipitate that forms when the following solutions are mixed. And the precipitate again would be either low soluble or insoluble. Insoluble / low soluble reveals or indicates precipitate formation. Okay, so barium sulfide and magnesium sulfate, what you would do is you would write it just like a two comboed dissociation reaction, but which of course is our double displacement reactions. And we get barium sulfide aqueous and magnesium sulfate aqueous, okay, produces, all right, barium sulfate solid, because with a sulfate, barium 2 plus is low solubility, i.e. precipitate forming, and okay, like no ions really, or very few ions are dissociated. And then of course we can only have one precipitate form at a time when a mixture of ionic compounds occurs. So that means our magnesium sulfide is going to be aqueous. And this solid precipitate barium sulfate is what then undergoes dissociation, that we will be actually calculating the equilibrium or the KSP constant for the dissociation of that solid. All right. Because remember, it's low soluble, it's not quite insoluble. So there is some ions being split apart in aqueous solution. And we're going to use our equilibrium knowledge now to quantify that. All right. And let's look at the B one. So ammonium hydroxide and iron 2 bromide are going to react in a double displacement precipitate reaction to produce one precipitate. Okay, now don't forget, sometimes you do have just completely free dissociated ions. That would not be a precipitation reaction. That would just simply be a double displacement physical reaction. But here we do see that iron bromide, okay, iron bromide will undergo a precipitate and create the following, undergo a switcheroo and create the following precipitate of iron oxide and solid, as hinted by this, that all other cations with OH minus are low soluble, and ammonium, okay, Br in two of them to be balanced. And let me balance my equation. There we go. So again, what you would see is when you merge your knowledge together, what we're going to find is we're going to be able to identify the low soluble precipitate form through a double displacement reaction, right? Where you have this solution. And you're going to now be asked in the next lesson to quantify the equilibrium process of our low soluble solids, low dissociation via KSP, solubility product or solubility ion product constant, for this particular context. So really good work, you guys. Hopefully that's a good review. And tomorrow we'll get right into the equilibrium connection for these problems. So great work.